particular next leading order calculation, and then I will try to generalize it from there. So again, there will be even more repetitions. If this really too much, let me know. But on the other hand, it is indeed important that everybody, this message really sink in, because otherwise this is really underlies everything else of the summer school. So to remind you, yesterday where we left off was to say we're going to examine this question of long distance and short distance physics using a concrete calculation at next leading order for this process of deep inelastic scattering with a virtual photon. There are two such sub-processes, and I point out to you that we are going to concentrate on this one because the calculation is the simplest and it illustrates the basic physics already, and we have only time really to discuss this in detail. But after we finish but these two, the nice thing is these two sub-processes don't interfere with each other. So this is an independent discussion. After that's finished, I will just mention how it works for this, for the other sub-process, and then we'll try to generalize from there. So I have already mentioned that the real calculation is therefore on this forward amplitude. When you do that, this is the result. You notice that the result is characterized in terms of the transverse structure function and the longitudinal structure function. This is, the G here denotes the fact that it comes from the gluon virtual photon. This is called the gluon fusion process. To distinguish it from the other diagram, which I'm not talking about right now. The thing to notice here, in addition to what I mentioned yesterday, that very important is this logarithm factor, is that for the longitudinal structure function, you see the leading term here does not have this logarithmic dependence. The log does come in, but when it comes in, it's proportional to the mass of the quark here at very high energies, of course. This is power law correction. This goes to 0 in the limit. This ratio is small. So as you can see, so you can again see that the divergences occur in different ways for the transverse and longitudinal, and that's something to keep in mind. So with that result, let's examine the physics, which is the fun part. The calculation part is mechanical. Everybody, as I said, should who've had a course on this should be able to obtain those results. Now, what we are really interested in is the Bjorken limit, high energy limit, in which you keep this ratio x more or less fixed. But in the recitation session, we already discussed that fact that x, even if you fix x, you can fix it at 0.1, 0.2, or you can fix it at 10 to the minus 4, 10 to the minus 5. The story are actually slightly different. But for the moment, let's imagine x is of order 1. And that's what traditionally we mean by Bjorken limit. What we are calculating here, the result I gave you, of course, is on the Platonic structure function. It's not the real hadronic structure function. We don't know how to calculate the structure function on the proton. So what I'm calculating is the structure function of basically a gluon initial state, right? From the diagram. And that has this logarithm factor. In the Bjorken limit, it goes like logarithm of q squared over m squared, which becomes very large, and then this factor of order 1. In the logarithm, of course, you can just separate this out. Now, the result is proportional to alpha, and then it's proportional to L. So the result actually is proportional to alpha times L. If you are in a high energy regime where q squared is much larger than m squared, whereas alpha, as you know, is 1 over logarithm of q squared over lambda QCD, and that product It's not small at all. That's what I mean by saying that if you only have asymptotic freedom in the theory, that perturbation expansion is still useless. Because when I calculate to the next order, the result is going to be alpha squared L squared. The product is of order 1, you don't gain anything. You can do a perturbation calculation if you have the strength to the third order, fourth order, but it doesn't do you any good. And that is why the other part, the infrared safety and factorization, is absolutely crucial for you to produce any prediction from QCD. All right? So the question is, then, can this problem, the fact that you have a divergent factor here, that you have expansion, effective expansion coefficient, which is 1, can this problem be isolated and controlled? If you can isolate this problem and control it in the same way we talked about, where you can find infrared safe quantities where the long distance part doesn't come in, then we'll have a game to play. Otherwise, there is no game. So the answer to the question is yes, we can do it. And of course, this is the gist of the factorization. The key ideas involved is that even if you have seen this large logarithm, you can, upon closer examination, you can find that this large logarithm is due to the collinear region of the, when you do the calculation in the momentum space integration, which of course it corresponds to long distance physics in coordinate space. And the long distance and the short distance physics can systematically be separated. That is the key idea. You can separate them, and the short distance part we can keep. The long distance part turns out to be universal. And these universal factors, once you isolate them, they are limited in number, and they can be determined, or they can be resummed into what will end up being just the part of the distribution functions, which is finite in number, which you can determine it phenomenologically. So that's the key ideas. I will show you how that happens. So go back to this calculation. Instead of just quoting the results, ask ourselves, how do we get the final result I quoted for you? Well, you have to calculate this Feynman diagram, you have integration over the final phase space. You have two propagators, one here, one there, and I won't go through the details. The integration you can do in, it's just the 3 momentum, since these are mass shell particles, just 3 momentum. You can organize your calculation in such a way, you do the longitudinal part of this integration first, you're left behind with the transverse momentum of this final state particle you're integrating over. Then these propagators can be shown to be just the energy, these factors here. See here again, the light cone coordinates comes in. This is basically the plus component and the minus component of the same. And when you have E squared minus longitudinal momentum squared, that's of course just the transverse momentum squared plus the mass. So this is the integration that's left. When you have, and then if you look at this, and this is a regular, this factor is regular. It doesn't have any particular features. The logarithm that we talked about comes basically from this factor. And in order to make that clear, you can do a change of variable into, you can take the logarithm of this as your integration variable. That's a trivial thing to do, of course. So then you end up with the integral over eta, which is like somewhat like a rapidity, actually, which has a range of integration from 0 to the end of their phase space, which is set by the overall center of mass energy, so logarithm of S. And this is basically a regular function integrating over eta over this range, so you can see this very easily. You can just plot it, such a integrand. What you're going to see is that This is the integration range from 0 to the largest factor, which is s divided by basically logarithm of s divided by n squared. When s is much, much larger than n squared, the integration range increases logarithmically. So where does that logarithm come from? It comes basically from a flat top here, where the range extends increasingly large when s becomes very